This video will give a technical overview of GridCAE. Grid computing is a service-oriented paradigm for sharing distributed resources over the internet. It primarily focuses on sharing compute resources and data storage, although it can also be applied to resources such as sensors and telescopes. Grid middleware, for example GridCAE, Unicore, G-Lite and Globus Toolkit, is open source software for managing networked computing and data resources. The cloud, or cloud computing, also provides access to on-demand computing. Cloud computing is growing fast and there are many providers, the biggest of which are probably Amazon with EC2, Google with App Engine and Microsoft with Windows Azure. The primary focus of cloud computing is providing scalable and flexible resources for web applications. Many cloud computing services are based on the use of virtualization, which allows users to choose their OS and libraries, whereas grid computing users are tied to the supplied software. Cloud providers guarantee spare capacity, meaning users can obtain resources almost immediately, whereas grid users will normally have to wait in a queue. GridCAE could potentially be used on either cloud or grid resources. Cloud will generally provide faster startup times, avoiding the waiting queues associated with grid. However, grid resources will typically process scientific computing jobs, such as CFD, much quicker given comparable hardware resources, clock cycles, once the job is underway. This is because most grid resources use HPC hardware that has been optimized for parallel computing work. In particular, the network connections between nodes are likely to be much faster in grid resources. Users of grid resources are dependent on the software they require being installed on the grid. In contrast, users are free to install their own software on cloud systems. Grid technology, such as the GridCAE middleware, offers features important to GridCAE. This technology could be adapted to use cloud resources in the future. GridCAE was developed for grid resources. GridCAE is a service-oriented infrastructure. It supports business-to-business collaborations across organizational boundaries. GridCAE is open source and available for free. GridCAE makes use of business models, processes and semantics to allow service providers and users to discover each other and negotiate terms for access to IT assets. By focusing on business processes, GridCAE enables users to provision for their computational needs more cost-effectively and develop new business models for their services. As the figure shows, we have the GridCAE client module at the client organization side and the service provider management and the basic application services modules at the service provider side. The engineer uses the GridCAE client to open an account through to the service provider management. The engineer then chooses an appropriate service level agreement, or SLA, and proposes it to the service provider management. The SLA proposal must be approved by the administrator to allow the engineer to proceed with the execution. The engineer is able to choose an application service provided by the basic application module using relevant services. Here the GridCAE client uses the data processing service. The billing and monitoring is done by interaction of the application service with the account service on the specific account of the user. CFD execution is a performance-oriented service with great computational demands. The different steps in a CFD simulation include CAD geometry preparation, mesh generation, solver setup, calculation and post-processing. The application workflow execution scheme that is used during the CFD process lends itself well to gridification. The example architecture can be distinguished by two principal levels, depending on the involved actors and roles. The first level is the end user, while the second is the service provider. An example end user is a CFD engineer. The infrastructure at this level consists of the CAD and meshing software. The infrastructure on the service provider, SP side, hosts the solver application. The interaction between those two levels is achieved through GridCAE, which provides a client as well as a service provider component. The The design of this architecture results naturally from the fact that the most computationally intensive stage within the CFD execution workflow is the CFD solving process. Consequently, the proposed architecture results naturally from the CFD workflow. This test case demonstrates the potential of grid computing to solve CFD optimization problems involving industrial applications. The geometry is a cooling duct located in the underbonnet region of a vehicle. Air flows through the left side grille, highlighted, into the cooling duct and towards the transmission. The figure shows a workflow for the optimization process. A model of the duct geometry is created using GridCAE software. A mesh is generated using *CCM+ software. GridCAE is used to submit the CFD analysis job to the grid environment. This is done using OpenFOAM software. The Mode Frontier application controls each software tool and establishes the optimal design configuration. The workflow shown is a Mode Frontier workflow. The architecture chosen for this specific case is shown here. As the end user, ICON's consulting engineers set up the complete CFD workflow using the Mode Frontier application. Appropriate software for CAD preparation and meshing, as well as the GridCAE client, are located within the local infrastructure. The GridCAE server located at NTUA serves the role of the grid service provider. The grid service is deployed in the middleware and is accessed from the end user through the GridCAE client. The job delivered to the service provider is forwarded to the high-performance computer for execution. Maxwell is a high-performance computer of 32 CPUs provided by EPCC. All jobs submitted by the end user to GridCAE server are finally delivered to Maxwell. We are interested in a high discharge velocity and a low pressure drop. A total of 450 design variations of the cooling duct were evaluated. The entire execution was performed in about 8 hours. This is twice as fast as a standard non-grid approach. The results obtained through the grid-enabled optimization process are consistent with previous solutions achieved using local resources at ICON. From the solution point of view, there is no real difference between executing the same models locally or remotely. Thank you for listening. For further information, please visit the Gridipedia website.